and not a window, entire screen. Okay, you can see my screen now, I hope.
Yes, sir.
Fine. So let's start. I will just quickly recapitulate what we did the last day. We started talking about Lie algebras, and the rest of the lectures before this had been something which led to the idea of Lie algebra starting from a Lie group. We saw that the way in which elements of a Lie group behave is more or less determined almost entirely by what happens close to the identity. And if you just look at elements close to the identity, in particular, you look at the behavior of one parameter subgroups, which are very close to the identity, then you end up with some tangent vectors to these one parameter subgroups at the origin or at the identity, actually. And these tangent vectors have a product called the Lie bracket defined among them, which can be written down in terms of the structure constants and so on. But from today and over the next few classes, we will essentially treat the Lie algebra itself as an independent entity. We will worry about the connection between Lie groups and Lie algebras later on when we finish our study of Lie algebras properly. Also, of course, the assignments that I've one of the assignments that I've given you already, and the next one essentially will be a way of figuring out the product rule for a Lie group starting from the structure constants, which essentially means the connection between a Lie algebra and the Lie group. But for the proper course, that is for the rest of the lectures, at least not for quite a few of the coming lectures, we will treat the theory of Lie groups, Lie algebras, without necessarily referring to the Lie group all the time. So, although for us the Lie algebra arose out of a Lie group, what we are going to do is treat a Lie algebra as a sort of independent abstract entity. And for that, okay, this was the definition. A Lie algebra is a real vector space. We will talk about complex Lie algebras later. In fact, we will actually have to talk about complexification of Lie algebras in order to get the theory correctly. And there's a very simple reason for that. Say, okay, let me just go off on a tangent right now and talk about why do you need complexification? If you had something real, why make it complex? Of course, complex doesn't mean complicated. It means why introduce complex numbers? And the answer to that is simply, is simply that suppose I wanted to figure out eigenvalues of a real valued matrix. Can I do that if I only stick to real numbers? Suppose you have square matrices which are real valued, all the elements are real. Say it's a 3 by 3 matrix, let's say a rotation matrix, for example. Can I figure out a spectrum entirely sticking to real numbers? Yes? What would your answer to that be? You're waiting for an answer. Can you find out? Okay, in other words, are all the eigenvalues of a rotation matrix? Is it possible for it to be real?
Sir, could you please repeat the question?
Suppose that I give you an arbitrary rotation matrix, which is a real valued matrix, all elements are real. I'm using that as an analogy to understand why we need to go to complexification of Lie algebras. That is, introduce complex numbers, whereas despite the fact Lie algebra is a real vector space. We'll talk about that in detail later, but for the time being, I'm just giving you a motivation why, despite the fact Lie algebra starts with a real vector space, but then we will go on to how to make it complex, in the sense, introduce complex numbers. So, as a motivation, basically, what we will do later is figure out eigenvalues, eigenvectors in a way. But a simple question is this: a rotation matrix, for example, an arbitrary rotation matrix, is definitely a real 3 by 3 matrix, right? You agree? All the
Yes,
elements are real. What about its eigenvalues and eigenvectors? Can I diagonalize the rotation or give any arbitrary rotation matrix? Other than the identity, the identity is of course a rotation matrix, rotation through zero. That can be diagonalized entirely sticking to eigenvalues and eigenvectors because one and only one is an eigenvalue and all vectors are eigenvectors, right? For the identity. You just apply identity on any vector, you get that vector back times one. So every vector satisfies that. But apart from this zero angle rotation, if you think of any other rotation, is it possible to solve this eigenvalue problem completely, sticking to only real numbers?
No.
Can you argue why not?
The only condition that we have is that the magnitude of the eigenvalue should be 1 for a rotation matrix. So it can be complex as well.
Magnitude of the eigenvalue has to be 1. So it can be complex as well. Okay, I don't disagree, but it can be complex and has to be complex are two different things, right? Can you argue that every non-trivial rotation matrix, that is every matrix where the rotation is not through 0 degrees, must have a pair of complex eigenvalues and hence complex eigenvectors? The answer is very simple, really. Just think of what an eigenvalue, or more importantly, think of what an eigenvector means. It means that when you apply the matrix on it, you get a multiple of it back, right? So what does a rotation matrix do? It rotates a vector. If it is an eigenvalue, if it's an eigenvector, then the rotated vector has to be the same vector times a number. So just think of what rotations do. What does a rotation do? It rotates a vector, right? So is it possible to get back that vector times a number? When you say it's a vector times a number, in 3 dimensions, it's easy to visualize geometrically. It's another vector in the same direction. The number is just a scale factor. Question is, when I rotate a vector, can I get that vector back, or at least a vector in that direction back? Is it possible? You rotate the vector and you get a vector in that direction.
It's either by pi or 2 pi rotation, depends on the sign of the eigenvalue.
Pi or 2 pi. I think you are confused. I'm talking about arbitrary rotation here. Forget pi or 2 pi. 2 pi, of course, is no rotation at all. I'm talking about arbitrary rotation. Then will it be possible to get an eigenvalue at all? If you have an eigenvector, it means that the resulting vector has to be in the same direction as the original vector. You rotate a vector, the direction doesn't change. Is it possible? Think of geometry.
only if the vector is axial, like
Only if the vector is along the axis, right?
yes,
Which means, and that vector will not change, which means you're going to get a factor of 1, right?
yes,
So every rotation matrix has one eigenvalue which is equal to 1, where the vector is along the axis. Okay? But any real vector which is not along the axis will definitely change direction. The simple geometry of rotations, right? Any vector which is not along the axis will change in direction when you apply the rotation. Unless it's a 2 pi rotation, in which case, of course, it's back to where it was. Clear? In other words, if the rotation is not 2 pi, there can be no other real eigenvector. A 3 by 3 matrix, of course, has 3 eigenvalues, and all orthogonal matrices are diagonalizable, which means it has 3 independent eigenvectors. But only one of them can be real. Any other real eigenvector would have meant that you have other vectors which don't change when you rotate. And that's impossible unless the rotation is through 0 degrees. Simple geometry. Any vector not along the axis must change if you're doing a non-trivial rotation. So only one independent eigenvector can be there with real components. Now, why is that important in this context? The basic idea is even if you have a real matrix, diagonalizing that will often lead to complex numbers, complex eigenvalues, and complex eigenvectors. Okay. So if you were to stick only to the real world, or only stick with only real vector spaces, eigenvalue problems cannot be solved in most cases. The same thing here, when you are dealing with a Lie algebra, it is a real vector space, but later on, we will have to introduce complex numbers inside the real vector space by a process called complexification, which is because you really want to solve something akin to an eigenvalue problem. We will come to all that later. For the time being, this is just a real vector space, and the space has a product. By definition, when you say vector space has a product, you mean that the product behaves nicely with respect to addition and multiplication by a scalar, which means it distributes nicely over addition and so on. In other words, it's a linear product. But this product for the Lie algebra has to have a special property. This product is also called a Lie bracket in the context of a Lie algebra. It's a map which takes L cross L to L, of course, takes two elements of the vector space to another element with these two basic properties. That the bracket is an anti-commutative product. If you change the order of the vectors going in, you get a change of sign. And it's also a non-associative product in a very specific way. The non-associativity is encoded by this equation, the so-called Jacobi identity. Of course, why are we insisting on this? Because we showed the tangent vectors to OPSs actually obey these properties. You can define a bracket between the tangent vectors to OPSs, and by which you end up with this. Both, of course, this anti-commutativity and the Jacobi identity. So, a Lie algebra is not an associative algebra, and it's not an associative algebra in a very specific manner. We also explained in the last class how, if you have an associative algebra, from that you can create a Lie algebra by essentially taking AB minus BA kind of products. But we don't really need to go into that any longer, because right now we are not dealing with how you can get the Lie bracket. All I'm saying is, suppose you have a Lie bracket, you have a product like this, what properties will follow from there? Okay. Any questions so far? Sorry. Okay, if not, let's move on. We also introduce the structure constants in the context of a Lie algebra. The Lie algebra being a vector space, it means you have a basis, or at least you have infinitely many choices of bases. Once you choose a basis, you take the Lie bracket between any two basis vectors, EI and EJ. The result, of course, has to be a vector. It has to be in L. So everything in L can be expanded in terms of the basis vectors. When you expand that, these coefficients in front of EK will depend, of course, on K, which component you're talking about, also on INJ. And so CKIJ, EK will be the result. And these CKIJs are called structure constants. And CKJI has to be minus CKIJ simply because of this anti-commutativity. Simply because, and similarly, because of the Jacobi identity, you will have a relation which the structure constant must obey. Here I am introducing a slightly new notation. When you have a sum, like so far we did not write the sigma, right? Because we were assuming the summation convention. That's still in force. But this is something different. When I write a sigma with some indices, three indices in particular in a round bracket, I mean that this is really a sum of three terms in which IJK, JKI, and KIJ come in that order. And it's a sum of these three terms. So you permute I, J, and K cyclically. That's what this notation means. This is not a universal notation, but many people use it. And this really means a cyclic sum of this quantity, this product of pair of structure constants with I, J, K interchanged cyclically added together gives you 0. This is a direct consequence of the Jacobi identity for the Lie bracket. It's actually called the Jacobi identity for the structure constants. Now, one quick question before I go any further. In this expression that we have here, can you identify which one are the free indices, which one are the dummy indices in this expression? Yes.
I, J, K, and M are free.
And what about L?
That's
Yes, they're dummy. Good. But I, J, K are being summed over, yet they're free indices. Are you sure? Anybody else can also chip in. I said I, J, K are being summed over. So are they dummy indices or free indices?
For all I, J, K, M, K, for all I, J, K, and M, this is true. So even summing it over will be 0.
Mm-hmm. Okay, the important thing, you're right. The point is I, J, K are not dummy indices because you're not really summing over I, J, K. You're not giving I, J, K values and you're summing them. Right? If L is a dummy index because L takes the value 1, 2, 3 up to R and you're summing up over all of them. So whether you have L there or U or V doesn't matter. I, J, K are actually free indices, as you rightly said, because you're not really summing over them. You're just finding 3 terms in each of which I, J, K are actually free indices, right? They're just written in different order. Okay? So everybody is clear of that. Because that will be very important for the assignment that is to come, not this one, the next one. That when you write a cyclic sum like this, the indices over which you're doing a cyclic sum are still free indices unless they're contracted somewhere else by something else. These are as a step free indices. That's not a sum over all possible values. Okay. So now we come to today's lecture. But before that, any questions about this? Ask quickly, then we will move on. If not, we will now start the study, a slightly detailed but not very detailed study of Lie algebras. We don't really want to go into all possible ramifications of the thing. That won't be necessary. But this is important. These issues will be important. One of the things is if you have 2 different Lie algebras, L and L prime, how do you decide whether they are different as Lie algebras or whether they are the same? Remember, when we say that they are different or the same, we are asking as Lie algebras, are they different or the same? Okay. So we are not saying are they the same vector space? Of course, they may not be. That would be a very easy thing to answer. The important point is I will say 2 Lie algebras are isomorphic to each other. Okay. Let me ask you, what would you define isomorphism of Lie algebras as?
if they're derived from the same
If they
associative
in
algebra.
Lie group,
No, I mean,
that would be rather trivial, right? And first of all, if you see either for the Lie group, you will get the same result, perhaps. Well, that perhaps is not really true because, by the way, you could start with a given Lie group, use different coordinates, then you'll get Lie algebras which look different, and those would definitely be isomorphic. That better be. But right now, we are not even talking about Lie algebras in the context of Lie groups. You have just been given 2 different vector spaces, L and L prime, on which 2 different bracket operations are defined, each of which is a genuine bracket. That is, obvious all those properties, these properties. Okay. Now, how do you decide that they are isomorphic to each other? Don't mention Lie groups here because we may not even bother figuring out whether this Lie algebra came from a Lie group or not.
No, I was talking about if they can be backtraced to the same associative algebra.
That would be actually pretty hard to do, number one. Although we did say that ultimately, if you have an associative algebra with a product star, and you defined a bracket operation on the same vector space which that algebra has, by A star B minus B star A being A bracket B as a standard commutator, then that will become a Lie algebra. So from an associative algebra to a Lie algebra is easy. The other way around, the fact that every Lie algebra has as its background an associative algebra is actually not very easy to prove. Even though it's true, it would be very difficult to construct the Lie algebra. And so this particular method would not really be very great. In fact, even associative algebras could also be, different associative algebras could also be isomorphic to each other. So this definition doesn't work with the associative algebra from which it came. And once again, although the algebras do come from associative algebras, all the properties can be figured out without worrying about which associative algebra it came from. So we are not even going there. Now, there's a very simple question. When these are things, these are sets, right? L and L prime are sets. With two sets, how do you say that they are isomorphic or they essentially have the same structure? When you have two different sets, how do you say that they have the same structure?
1-1 correspondence.
We have a map which is an isomorphism.
Well, that's map which is an isomorphism is jargon. Okay.
A bijective map.
Yeah, 1-to-1 correspondence, bijective map, that's fine. But map which is an isomorphism is actually more precise, but you need to define what an isomorphism is. First thing, you need this. If you just worry about the set, then this, sorry, not an isomorphism, this has to be there has to exist a bijection or a 1-to-1 correspondence, essentially the same thing, between the two sets. Without that, question of the sets having the same structure doesn't even arise. Okay. However, when you say it's an isomorphism, say when you say it's a Lie, say when you say it's a group isomorphism, you don't really just want a 1-to-1 onto map. What you want is a 1-to-1 onto map which respects the structure of the group. That is, which respects the product. You multiply elements first, then apply the map. Or you apply the map first, then multiply the resulting elements, you get the same result. Right? That's what a group isomorphism is. When you talk about a linear vector space isomorphism, you're really talking about a 1-to-1 onto map, that is a bijection, which preserves the basic structure which is there in a linear vector space. What is the basic structure in a linear vector space? That's linear combination. So linearly combine first, then apply the map, or first apply the map to individual elements, then linearly combine by the same factors, you get the same result. That's a linear vector space isomorphism, which we simply call a linear map. So basically, when you are saying a map is an isomorphism, what you mean is that it has to be a map which has to be a 1-to-1 onto map, has to be a 1-to-1 correspondence, but beyond that, it also has to be something which preserves the basic structure of the object we are looking at. And in the case of a Lie algebra, what is the basic structure? In fact, this bijection has to be a linear map because one of the basic structures that a Lie algebra has is that it's a vector space. So this map has to preserve the linear structure which the vector space has. So any isomorphism, any map phi, which is going to help us establish that L and L prime are isomorphic, must be a linear map. But that's not all. What is the other major structure which Lie algebra has, which
The
distinguishes
Lie bracket.
the Lie bracket, because that's what makes it different from just any vector space, right? So basically, you have to have something like this. You take two elements x and y from L, form the Lie bracket, that gives an element of L. Apply phi on that. What you should get must be the same as you apply phi first on x and on y, and take the Lie bracket of these two. Notice the two brackets here may very well be different. This bracket is the bracket in L. This bracket is the bracket in L prime. But this map phi has to be able to do this, that whether you apply the map first or afterwards, here you're doing it first and then taking the bracket. Here you are applying it after calculating the bracket. Either case, you get the same result. That ensures that basically whatever Lie bracket operations you do on one set can be replicated entirely on the other set. Okay? Clear? So this is your Lie algebra isomorphism. Two Lie algebras are called isomorphic, which means essentially that's the same as Lie algebras. If not, is that if you have an invertible linear map between them, a bijection, which is a linear map, which is a bijection, of course, is an invertible linear map, which preserves the Lie bracket structure. Okay? And then you essentially say L and L prime are the same. Actually, although I did say that we will not talk about groups and the connection with algebra, I would still point out that if two Lie groups behave identically near their respective identities, then they will give rise to, well, we have been saying same Lie algebra. Basically, they give rise to two algebras which are isomorphic to each other. Frankly, as far as Lie algebras are concerned, isomorphic means essentially the same. Okay. Now, this helps us establish how when two Lie algebras are the same. That's one of the, whenever we're looking at a new kind of algebraic entity, these are the things we need to look at. We need to look at when would you say two things are the same. If there is, in this case, if there is a Lie algebra isomorphism between them. Of course, we will not say Lie algebra isomorphism over and over again. We will just say isomorphism because we are dealing with Lie algebras throughout. Of course, if we were dealing with a situation where we have to deal with different kinds of objects, then isomorphism may mean different things depending on what object you're talking about. Is that clear? But it always boils down to the same thing in the sense that the isomorphism has to preserve the basic structure of this object, whatever mathematical object you're talking about. Okay, so I said whenever you're looking at a new kind of algebraic entity, you should look at this. When do you call them the same? There are other things also that you must always look at. What is another important thing that you must always look at whenever you're looking at a new entity? In fact, we talked about that when we were doing groups and so on. What's the other major thing that you should first look at and first establish that you understand properly when you're talking about a new kind of mathematical structure? When do you say two such structures are identical, that is isomorphic, that is definitely the first thing you should decide upon, because after a lot of what you're going to say is this is the same as that, or this is not the same as that. You need to know exactly what that means. And the other major thing that you should look at, we have already talked about that several times, is substructure. The first thing you look at a set, when you understand a set, is when you say two sets are identical. The second thing is when you say one set is a subset of the other. For groups, the second important thing beyond establishing when do you say two groups are identical, there is group isomorphism, is subgroups. Similarly here, we are going to look at the notion of a Lie subalgebra. Of course, we will just usually call it just a subalgebra, not a Lie subalgebra, because Lie is sort of understood in all this discussion. So now, help me out here. How would I define a Lie subalgebra? What kind of thing would I look at? L prime has to be a subset of L, of course. But a subset of L with what properties?
Then closure.
Closure means closure under some operation. Which operation?
Closed under the Lie bracket.
Well, actually, you're right, but even before that, you have to look at closure under linear combinations. Remember, Lie algebra is, never lose sight of the fact that Lie algebra is at its heart a vector space. Then it has a Lie bracket. Both of these structures are important. It's not just something which has a Lie bracket, or it's not just a vector space. It's both vector space and with the product operation. So it has to be, L prime has to be closed under both of these structures. That is, one is linear combination. In other words, L prime has to be a vector subspace of L, and these are both closure statements. This is closure under linear combination, and then what you are saying is this, closed under the Lie bracket. In other words, L prime is a subalgebra. Of course, when you say closed under Lie brackets and put that first, is because you're focusing on the subalgebra part. But it's also a vector space before that. You have to always bear that in mind. If it's a Lie subvector space with this property, for all x, y belonging to L prime, the bracket x comma y has to belong to, yes?
L prime.
Prime. Right. Close. That's the closure. However, okay, not however. While I kept on saying that I will not talk of Lie groups, it's very hard to resist talking about the Lie group leading to a Lie algebra at this stage. In fact, if, say, G is a subgroup of G prime, or if G prime is a subgroup of G, let's say, Lie, they are both Lie groups and G prime is a Lie subgroup of G. Then L prime, which is the Lie algebra of G prime, will be is a subalgebra of L. So many things which happen at the Lie group level many of the group structures get reflected at the algebra level. This is one example. Now, when we dealt with Lie groups, or when we dealt with group theory in general, one kind of subgroup was very important. Remember what that was? Among all subgroups, one special kind of subgroup was very important in our theory.
The normal ones.
Sorry, I could hear you. One by one. Because you two, both of you,
Normal subgroups.
exactly. Normal subgroups were very important. That is, a normal subgroup is one in which G and G inverse is equal to G. Sorry, equal to N. For all G. That is, take any group element whatsoever, take any element from the normal subgroup, form this G and G inverse thing, the small n G inverse thingy, that will be in capital N. Now, that has an analog at the level of Lie algebra. Why that's an analog will be, why that is the analog is something that will be clear once you understand the group algebra correspondence more clearly. For the timing, I'm just stating this as a definition in Lie algebra theory, which is a subalgebra L prime, subalgebra of L. Note that this alone does not make N a normal subgroup. You have to establish that N is a subgroup and which has this property. If N is not a subgroup, then this will not help you say that this is a normal subgroup, of course. So it has to be a subgroup first, then has to have this property, this invariance property under conjugation. Well, a subalgebra L prime of L is called, its name is slightly different, although some people do call it a normal subgroup, normal subalgebra, but more often it's called a invariant subalgebra. Sometimes also called an ideal. So there are many names for the same thing. Invariant subalgebra is the more common one, perhaps. Ideal is also pretty common. Normal subalgebra is not very common, although that would be a perfectly natural name to give because it's basically akin to normal groups. Where basically what you say is something like this. It's again closure in a sense under the Lie bracket, but a more general closure than this. Here, what we are saying is if X and Y both belong to L prime, the bracket will belong to L prime. That's the subalgebra definition. This is more strict. You are saying for all X belonging to L prime and Y belonging to L, anywhere in L. This is what is extremely important here. Then, if you take the XY bracket, notice if X and Y both belong to L prime, then by virtue of L prime being a subalgebra, the bracket would have to be in L prime. But the speciality of an invariant subalgebra is, as long as one of the elements of the bracket belong to L prime, either X or Y would have done, I just chosen X, and the other is an element anywhere in L, this will belong to L prime. Okay? Clear? Just to remind you of the analogy, say if you had an element H in a subgroup, another element H prime from the same subgroup, this will definitely belong to H, right? That's just closure. But if your subgroup is such that you take H from the subgroup, but G from anywhere in the group, and still this belongs to H, then you say that H is a normal subgroup, right? Very similarly, here, if you take X and Y both from L prime, the bracket has to be in L prime. But here, this is more restrictive. You take X from L prime, and that's enough. Y can be anywhere in L. The resulting thing has to be in L prime. If this is true, then what you have is an invariant subalgebra. Of course, not all subalgebras are invariant. That's why there is a special designation. Any questions? Okay, now,
Sir,
yeah, go ahead.
so the conjugation operation and this Lie bracket operation are here the same. Right?
Not the same. I'm saying, right at this stage, the conjugation operation is something you do on groups. The bracket is something you do on an algebra. There are two entirely different operations. There is a connection. The connection essentially is, okay, once again, I should not really talk about the connection because, frankly, establishing this properly would need a proper algebra to group correspondence. But remember, we talked about this, that these tangent vectors T were elements of the Lie algebra, and the group elements were something like this, right? Okay. Now, if you take an element and do a conjugation, you get something like exponential u, exponential t, exponential minus u, right? Clear? That's the analog of GHG inverse. That's not the analog. This is GHG inverse. But exponential u, if you then think of exponential as something like 1 plus u square, etc., you get this 1 plus e dot dot dot, 1 minus u dot dot dot. And then you get, apart from identity, you get 1 plus ut minus tu, the kind of bracket, right? These are related to each other. I'm saying that if you look at the behavior of elements close to the identity, then conjugation of this kind essentially gives rise to a Lie bracket among the tangent vectors that were involved. That is why these two notions actually go hand in hand. If a Lie group has a normal subgroup, its Lie algebra will be an invariant subalgebra of the original algebra of the original Lie group. But frankly, even if you don't worry too much about this, that will do, because there's a connection between groups and algebras. I'm just showing that this is what you call normalness in a group, and this is what you call normalness in a subalgebra, in a Lie algebra. And there's a connection between that. Connection is simply this. For subgroups, conjugation keep you inside H only if you take elements both from the subgroup. For normal subgroups, conjugation keeps you within H even if you use G from outside. Just think of what happens at the subalgebra level. Bracket keeps X and Y bracket inside L prime if X and Y are both from L prime. But for a normal subalgebra or an invariant subalgebra, X and Y stay inside L prime. The bracket stays inside L prime, even if Y is anything in L. Just like this will stay inside capital H if G is anything in the whole group. Just think of that as an analogy right now. When you look at the correspondence between groups and algebras properly, after we do this reconstruction business fully, then you will see that there is a reason why normal subalgebras come from normal subgroups. Right now, you don't have to think of that. You just think of the analogy of that. Do you understand why I'm saying that this is analogous to this situation? For this to work, you needed H prime and H both to be from the group, from the subgroup. For this to work, which is true for a normal subgroup, G can even be outside the subgroup. Here, X is in the subalgebra, Y may or may not be, bracket is in the subalgebra. This is the analogy. Clear? Did it make it more confusing, or is it okay?
Yes, sir. It's okay.
Okay, now comes something which is slightly more complicated, which is, I don't know whether your linear algebra classes has handled this. You have two vector spaces. Say you have vector space V, and W is a subspace of V. Did you talk about the quotient space V by W? Do you know what V by W is? We have talked about quotient groups for groups. My question is, do you know what V by W, the quotient of a vector space by another, means? Yes or no? So you should either say yes or no. I should know. Which one?
Sir, kind of yes.
Kind of yes. Okay. Kind of yes. Well, let's not take kind of yes to be yes. Although I'm pretty sure most of you have known about this, but let me just remind you of that then. Look, whenever you say quotienting is being done of one object with another, you essentially are doing something called identification. You are essentially taking multiple elements of V, clubbing them all together, talking of them as the same unit. Okay. And of course, when you are clubbing them together, you're clubbing them together using some kind of equivalence principle or some kind of equivalence relation. And of course, W has to play a role in that equivalence relation. So, and that's true whenever you say quotienting. Okay. In any case, just think about all the quotientings you have ever learned about. Say, even in abstract topology, when you say a cylinder is a rectangle with a quotienting operation where you identify two edges, you're essentially saying, okay, take a rectangle, identify these two edges, treat all points on this point in this edge as the same as this point on this edge, and that quotienting operation gives you a cylinder. When you're saying, I'm going to find a factor group, you essentially treat cosets as elements which means all the elements of the coset, which are different elements, you are grouping them together as a single element. Here also you do the same thing. So this is really set of equivalence classes. Where what is the equivalence relation? The equivalence relation is simply, so this is the set basically, and the equivalence relation here is okay. Of course, when you say equivalence class, it means all elements which are equivalent in V to V put together. And the equivalence is simply this: V and V prime are equivalent if, of course, W has to come somewhere. The difference V minus V prime belongs to W. That's the definition of equivalence in this used in this case. And when you group them all together, you get a set, of course. But what's so special about this set? Is this just a set, or does it have other properties? Like say when we did quotient groups, we were careful only to actually quotient it out with respect to normal subgroups, right? We didn't do G by H. We could have, and would have got a structure, but we actually did G by N and then got a quotient group. Why? Why did I have to quotient out with a normal subgroup and not just any subgroup? Yes? The idea was simply to ensure if you quotient it out with G by H, that is, you just took the cosets with respect to H as separate elements, you would definitely get a new set. But you would not be able to define a group relation. You will not, that G by H will not become a group. It will become a group only when what you're quotienting it out by is a normal subgroup. And that is why G by N is called a factor group. This is just called a quotient space. If you do this, you can do this, but this will be called a quotient space. It's not a group. But when you factor out by a normal subgroup, you get a quotient group. Similarly, you have to initiate, if you want to call this quotient space, but in this case, remember we are dealing with vector spaces. So we would love this to be a vector space, right? Okay, how do you check whether it's a vector space? How do you check whether any set is a vector space? Yes? Given a
We
set,
need to first define
exactly. You cannot
addition
even check. You have to first define definition, define what addition means. But here it should be obvious what addition means. Because there's no other natural choice. What should this be?
Equivalence class of V plus
V plus W. And what should C times V be?
equivalence class of CV.
Right. But before you even begin to check whether this set, which is a set of such equivalence classes, becomes a vector space under this definition, the first thing you should do is check something else, which is
well-defined.
which is whether these are at all well defined. Pretty easy to check that they are. That is, well defined means if instead of taking V, you have taken V prime from the same equivalence class, you have taken W prime from the same equivalence class, then you would of course have got V prime plus W prime instead of V plus W. And you would have to show that the equivalence class of V prime plus W prime is the same as the equivalence class of V plus W. In other words, this is a well-defined definition. Doesn't matter which element of the class you pick out. Same for this. Okay, I'm going to assume that you know how to do this. I'm pretty sure you all know, or even if you did not do this before, you should be able to easily figure out that this is a well-defined vector space. But remember, we are not talking about just vector spaces. We are talking about Lie subalgebras. This is an invariant. So if we have L prime is a invariant and subalgebra, of course, a Lie subalgebra of L, then first of all, you can of course form the vector space L by L prime but you're not interested in that being just a vector space, right? You're dealing with Lie algebra. So can you make it a Lie algebra? How can you make it a Lie algebra? We have already seen that since L prime is a vector subspace of L by L prime is a genuine vector space. At least we have not seen that, but I'm pretty sure we have seen the proof before. If you haven't, you should be able to easily reconstruct the proof using that addition and multiplication by scalar. But how would you make this into a Lie algebra? For that, you need to define. You already know it's a vector space, right? To make it a Lie algebra, what would you need to do? You need to define a Lie bracket. Okay? That is, you have to be able to define, take X, an element of L, where X is not an element of L, by the way. X is, the square bracket of X is an element of L by L prime, the equivalence class. And again, here, what does it mean? If it means X and X prime are in the same equivalence class, provided X minus X prime belongs to L prime. And why? I should be able to define a Lie bracket between them. Now, unfortunately, you have too many square brackets, but you have to realize a square bracket with a comma is a Lie bracket, and a square bracket with just one entity is a equivalence class. So this, how would you define a Lie bracket between this and this? Which of course has to be an element here, right?
The equivalence class of the Lie bracket of X and Y.
And, well, that's about the only thing you can do, right? You don't have much choice. If this is not the right answer, then nothing is the right answer. This is the obvious choice, but is it at all right? Okay. Several things. The first thing you should check, okay, this is not a homework, this is something we should do right now. Which is this definition even well defined? Okay, then we will have to see whether it actually is a Lie bracket. That is, it looks like it might be, but is it? That is it really anti-commuting, and does it satisfy your Jacobi identity? Anti-commuting is trivial to show. The Jacobi identity takes a bit more work. Both of them are pretty easy to show. But what really needs to be shown even before this is that this actually makes sense, this definition. Why? Because we're saying to find the Lie bracket of these two equivalence classes, you take an element from the first one, X, take Y from the second one, find the Lie bracket and find the equivalence class of that. But of course, what you could do is take an X prime, which belongs to X, not X, some other element, Y prime, which belongs to Y, again, not Y, some other element, and take an X prime, Y prime, and form its equivalence class. And nobody would blame you if you did that. After all, nobody said which element X to take. Just take something which is in the equivalence class. So if this thing ended up giving a different equivalence class from this thing, then you're dead. Then this definition makes no sense, right? So how do you proceed? You proceed by doing this. X prime minus X has to be an element of L prime. Let's call that lambda prime. Or lambda, let's call it lambda, which belongs to, lambda belongs to L prime. Y prime minus Y is mu, let's call that. And mu also belongs to L prime. That's the definition of X prime and Y prime being in the same equivalence class as X and Y respectively. So X prime, Y prime's bracket has to be X plus lambda bracket, Y plus mu bracket. And is this the same as X comma Y? Of course not. Right? This is X comma Y, but you have three more terms. Now, this is where the importance of L prime being a invariant subalgebra comes in. L prime being a subalgebra means this thing definitely belongs to L prime, right? Two elements from the subalgebra, take the bracket, has to be there. But what about these two? Hmm? Yes?
Belong in L prime.
Hmm? They will also be in L prime. They will also belong to L prime, but that's because L prime is an invariant subalgebra, right? If L prime had not been an invariant subalgebra, but just a subalgebra, then all that is guaranteed is that L prime is closed under brackets, which means take two elements from L prime, you get an element of L prime. But here, each of these three brackets are elements of L prime. The last one simply because L prime is a subalgebra. The other two because L prime is an invariant subalgebra. So if any one element of the bracket is in L prime, the bracket's result is in L prime. Of course, these three things together, each of these three are in L prime, so their sum is in L prime. So you can see that this bracket and this one differ by an element of L prime, which means they belong, these two brackets belong to the same equivalence class. They're equivalent to each other. So their equivalence class is the same. So this is a very defined thing. What I would stress here very much is that L prime being an invariant subalgebra is very, very important. Without that, L by L prime would not have been a well-defined Lie algebra. The Lie bracket itself would not have been properly defined. Clear? Any questions? And L by L prime is obviously called the factor or the quotient algebra. Can only be defined if L prime is an invariant subalgebra. Otherwise, L by L prime is a vector space, but will not be a Lie subalgebra. Okay. And one more thing which is extremely important is that there is one kind of invariant subalgebra which a Lie algebra automatically has, and this is the following. Given a Lie algebra L, you define a subalgebra for this. It's called the commutator subalgebra, also called the derivative subalgebra. You can just call the derivative of L often. So this subalgebra, we are going to call this L with a lower one. We'll see why that's important. Of course, you are calling this L with a lower one and not just L prime. It of course implies that somewhere in the picture there's L2, L3, L4 waiting to come in, right? L1 is defined to be okay, the name is the commutator subalgebra. So what do you think L1 would be? Just from the name, what would your guess be? The set of what? Commutator, by the way, is a name which you are using here, although the Lie bracket is not a commutator, not have to be, but you also see that every Lie bracket ultimately is a commutator AB minus BA for some invariant underlying Lie algebra, right? So although we introduced the bracket as an independent operation and not here as a commutator, the name commutator in this subject, in this definition is very suggestive. So is this enough?
The equivalence class of identity or something.
No, it's much simpler than that. All right, or more complicated than that, depending on the point of view. The definition is simpler. It's a set of all brackets x comma y for xy belonging to L. Okay, take elements from L, form the brackets. That's it. That gives you this commutator subalgebra. Instead of all brackets, all results of the bracket operation. Is that clear? Should not be, because there's not the definition. Is the set, okay, this is the span of, not the set of. That means you take all the brackets, form all possible linear combinations. Okay? We will see why you need a span instead of set soon, but let me give you an example to make this a bit clearer. Okay, name an algebra that you know, some simple D algebra that you know. That is, of course, you have done quantum mechanics. So from quantum mechanics, what kind of D algebras have you seen? Okay, even if the name
Angular,
angular momentum,
Angular
right?
momentum.
That actually is not a real D algebra, really, because of course this ILZ thing, that's this I. But that's simply that is a matter of complexification. There's an underlying real D algebra which has been complexified by deliberately putting in i's. Let's not worry about that too much. So if you take this D algebra with these commutators, of course these are Lx, Ly, Lz are the basis vectors. Actual elements of the vector space are all combinations of Lx, Ly, Lz. Now, if you form all possible commutator brackets of this, the set of all possible commutator brackets of small SO3 or small SU2, which are the Lie algebras. Small is for the Lie algebra, capital letters are for the Lie groups. So, Madam, I'm not sure. She was there somewhere. So this small SO3, small SE2. These are, both of them actually have the same Lie algebra. That's why you can call this both SO3 or SU2. But what is the commutator subalgebra here? If you form all possible brackets, what are you going to get? That is, take any arbitrary combination of Lx, Ly, Lz, take another arbitrary combination of Lx, Ly, Lz, form the bracket. Bracket here means just a commutator. What are you going to get? If you take all such things together, remember your original subalgebra is all possible linear combinations of Lx, Ly, and Lz. We took all the brackets and did their combinations. Of course, this is not the only bracket. There's the Ly, Lz, giving you Lx, and so on. And for the time being, let's just drop the I. Because the I's are artificial things which we put in for our physics purposes rather than anything else. If you had an algebra like this, Ly, if you form all possible combinations of Lie brackets, what would you get?
Get the same
Get
algebra
the same
back.
set back, right? So for SU2, the commutator subalgebra is SU2. Okay, nothing new. Clear? Because all elements of SU2 can simply be found as commutators of whatever element, some elements of SU2. That's pretty easy to see. Because the basis vectors, after all, you can get the basis vectors back, Lx, Ly, Lz back by taking commutators. They're done. So this doesn't give you something very interesting as a commutator subalgebra. It gives the same thing back, which, by the way, is a very important result. It is very important in classifying this particular Lie algebra as something very special, but as a special kind of Lie algebra. But we are going to come to that classification in the next class. But let's give you, okay, can anybody give me another example of a Lie algebra which you have in quantum mechanics? You must have seen plenty of examples. Angular momentum is not the only one of them. In fact, another in which you have explicitly real coefficients as well. Nothing else comes to mind. Just think of important commutator brackets that you know of in quantum mechanics. What other important brackets do you know of in quantum mechanics?
Spin.
Speed is the same thing. Same algebra. Nothing
X and
different. X and P, right? But X and P, okay, or A and A dagger, essentially very similar, except that A and A dagger has the advantage that it has real things. But do A and A dagger form the basis of an algebra? Or in other words, when you take a bracket of A and A dagger, do you get some combination of A and A dagger?
No.
No, you get one, right? So to get a Lie algebra, your basis will not be A dagger alone. It will be A dagger and 1. Could be 1, could be half, I don't care. I can just use 1, right? So when you want to talk about the full Lie algebra, then not only talk about the bracket commutator between A and A dagger. This is called the by the way, this is called the Heisenberg algebra for a very obvious reason. But when you talk of all possible Lie brackets between basis vectors, you really need to talk about all possible Lie brackets between the Lie algebra elements. But if you know the basis, then just the basis will do, right? We already have seen that if you know the basis vectors and their Lie brackets, that gives you the structure constants, and that tells you all possible Lie brackets. But you also need these brackets. I don't bother saying 1 and A or A dagger and A because we know what they will be because of the antisymmetry. In this case, they're simply 0. Okay? Right? So the Heisenberg algebra is all possible linear combinations of A dagger, and when I say 1, I mean the identity, right? All 3, any combination. All possible combinations give you elements of the Heisenberg algebra. But if you form brackets of any such 2 elements, what are you going to get? Not just the basis elements, but any element. Alpha A plus beta A dagger plus gamma times 1. Commutator with alpha prime A plus beta prime A dagger plus gamma prime 1. What is this bracket? Help me out. What is the value of this bracket? Come on, this is easy.
Alpha beta minus
It's not
beta.
alpha. It cannot be alpha beta because
Alpha prime.
Beta prime. Sorry.
alpha beta prime minus beta alpha prime times 1, of course. Right? And it's easy to see that all brackets will be multiples of 1. So remember, multiples of 1 actually is a subspace. Right? This original thing is a 3-dimensional vector space. If you take all multiples of one of the basis vectors, you get a 1-dimensional subspace. So in this case, for the Heisenberg algebra, the commutator subalgebra is the 1-dimensional subalgebra, not the whole space. For SO3, SU2, the commutator subalgebra is itself. For the Heisenberg algebra, it's actually it's 1. Okay? And it's multiples. Clear? In fact, if you took X and P, with X and P, you would have to take the identity as a third element, right? Because XP and identity, they form a closed thing. And this will give you very similar cases. And again, there also, when you form the subalgebra, or from the commutator subalgebra, you will get just multiples of the identity, nothing else, right? So the commutator subalgebra in different cases can be very different. We will see they happen to be very important in the theory. So we are going to explore them in detail in the next class. But for the time being, let me just point out one more thing. So if you start with the Heisenberg and form Heisenberg's derivative or commutator subalgebra, Heis 1, then you can form Heis 2 by forming Heis 1 with Heis 1. That is, take all bracket of this commutator algebra, form brackets between them. But what will happen if we did that now?
0.
Then you'll just get the invariant subalgebra, which has just the 0 element, nothing else, right? So basically, this is something we are going to explore in detail in the next class, but basically L gives you L1, which is suggestively written as L comma L, which means take all possible brackets, take all possible linear combinations of them. Then you have L2, which is L1 comma L1. Then you have L3, which is L2 comma L2. In general, you have Lj plus 1, which is Lj comma Lj. If you started with L equal to SU2, then L1, L2, L3, all of them will be SU2, right? Clear? First time you're essentially doing the same thing over and over again. So if the first time you get SU2 back, you'll keep on getting it back. On the other hand, for the Heisenberg 1 is identity. Do it second. So if L1 is the Heisenberg, L is the Heisenberg. L1 is spanned by the identity, all terms of this kind. L2 is 0. Okay? Hi. So in this sequence, if it so happened that the sequence leads to 0, you say that the algebra is solvable. That's a very special kind of Lie algebra. The name, you don't have to worry about why. The solvability name comes essentially from the fact that Lie algebras were very useful in solving differential equations. In that theory, solvable Lie algebras plays an important role. For us, the only thing is to remember that this sequence of algebras terminates at 0. If it does, it's called solvable. If it doesn't, then the only possibility is somewhere down the line, not necessarily the first step, but somewhere down the line, the same set should keep on coming back. Same non-zero set should keep on coming back. So that's a non-solvable algebra. This one is a solvable algebra. Next day, we are going to look at a bit more in detail at this and other properties of the commutator subalgebra and other kinds of classifications of Lie algebra, which will be very important for us to figure out the structure of not all possible Lie algebras, but the kinds of Lie algebras that we will need in physics. We can actually do a full classification of those Lie algebras, so that if you once learn that, you essentially can handle all Lie algebras under the same sort of setting. Not all Lie algebras again, only those that are important for physics. Okay. If there are questions, ask. If not, we will fold up today. If not,
So unsolvable ones are where the sequence doesn't terminate, right?
the sequence doesn't go to 0. The sequence just repeats at some other value. Say for SU2, it keeps on going SU2, 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 SU2. That's not a solvable one. Solvable means this sequence terminates at the trivial algebra. There are other cases where you start with L, then you get to L1, then you get to L2, but L2 is the same as L3. So it keeps on repeating. And L3 is not 0, but it keeps on repeating. That will be non-solvable. Okay. So these designations, frankly, physics don't bother too much about solvable algebras because we are specifically interested in a special kind of algebra which is definitely not solvable. For most of our work, at least in particle physics, the kind of algebras we need are not solvable, which is not a bad thing, which is actually a very good thing for us. But if you're doing things like string theory or applying Lie groups to condensed matter physics, very often solvable algebras come in. So it's not true to say that you don't never need solvable algebras, but you don't need solvable algebras very often. So our interest in the solvable algebras is to show that the things that we are going to deal with mostly are not. As a mathematical entity, they are very important, but as a physics interest is sort of small. What is more interesting are the ones which are not solvable. Okay, any further questions? If not, let's call it a day today. I will see you on Wednesday then. And by the way, I cannot upload this video right now. I will do it around Wednesday because I don't have good enough network connection right now. Okay. Bye.